Lesson 5-2 Relations, and in this lesson you learn to identify the domain, range, and inverse of a relation, and to show relations as sets of ordered pairs, tables, mappings, and graphs. Now, why is it important? Because you can use relations to solve problems involving economics and probability. Let's take a look at this example in biology. There are 1.4 million classified species of microorganisms, invertebrates, plants, fish, birds, reptiles, amphibians, and mammals. Recently, 930 species worldwide were listed as endangered. A species becomes endangered when its numbers are so low that the species is in danger of extinction. Okay, so in the United States, the manatee, an aquatic mammal, is considered to be endangered. In the table below, you'll find the number of manatees that have been found dead since 1981. Manatees are mostly found in Florida, okay, and uh, this is a mammal that is a very gentle mammal that is endangered of becoming extinct, okay. And let's look at this table. So in 1981, there were 116 manatees found dead, 1982, 114, and so on and so forth, all the way to 1998. In 1998, there were 231 manatees found dead. Okay. Now, looking at this table, you can also represent this table in another way. So what you can do is the manatee data could also be represented by a set of ordered pairs as shown in the list below. The first coordinate is the year, and the second coordinate is the number of manatees. Okay, each ordered pair can then be graphed. Okay, so if we take this information right here, okay, and put it into ordered pairs, okay, we can start with 1976 and 116. So 1976 is right around here, and 116 approximately there. Okay, 1982, 214. Okay, 1982, and sorry, not 214, 114. Okay, these are just approximations, obviously. 1983 and 81. Okay, 1984 and 128 right here. Okay, 1985 and 119, 1986 and 122, and so on and so forth. Okay, so you can see here 1990 and 206 is right over there. Okay, and we have all the way to 1991, 92, 163. Okay, and 1993 is 145, 1994, 193 dead, and it jumps to 1995, 201. Okay, 201 for 1995, and 1996, 415. That's a big jump right there. So 1996 should be around that area, 415 manatees found dead, all the way to the last one, 1998, at 231. Okay, now why is this important? What does it have to do with what we're trying to learn? Remember, the title of the lesson is a relation, and if you notice, there is a relationship between the year and the number of death found, the number of manatees found dead for that particular year. So these two numbers are related to each other. Okay, so we need to recall that a relation is a set of ordered pairs, like the one shown on the previous page. Okay, the set of first coordinates of the ordered pairs is called the domain of the relation. The domain usually contains the x coordinates. The second set of ordered second coordinate is called the range of the relation. It usually contains the y coordinates. So we'll define, okay, the domain and range of relation as the domain of the relation is a set of all first coordinates from the ordered pairs in the relation. The range of the relation is a set of all second coordinates of the ordered pair. So basically, your domain is your x coordinates, and your domain and your relation, okay, are your y coordinates. So your x coordinates will be your domain, and your y coordinates will be your range. So for the relation representing the manatee data, the domain and range are as follows. If you notice, the domain represents all the years, so 1981 to 1998, and the range represents all the manatees found dead for that particular year. Okay, so in addition to ordered pairs, okay, tables, graphs, tables and graphs, a relation can be represented by mapping. Definition of mapping, or a mapping illustrates how each element of the domain is paired with an element in the range. For example, in the relation 3, 3, negative 1, 4, and 0, negative 4, you can be modeled in each of the following ways. Remember, we can model this as an ordered pair, such as this one, 3, 3, negative 1, 4, 0, negative 4. We can put it into a table as well. Okay, x, y, 3, 3, negative 1, 4, negative 1, and 4, 0, negative 4. We can even graph this, what we learned, okay, plotting all the 3 points. And finally, the last one, we can map this. Mapping is very similar to a table where you have all your x coordinates here, or your range domain values, and you have your y coordinates here, or your range values, and you simply put an arrow to indicate which ordered pair or which x coordinate corresponds with which y coordinate. Okay? Let's take a look at example 1. In example 1, represent the relation shown in the graph at the right. Okay? A as a set of ordered pairs, B as a table, and C as a mapping. Then determine the domain and the range. Okay? So set of ordered pairs for A. These are your set of ordered pairs, negative 3, 3, negative 1, 2, 1, 1, 1, 3, 3, negative 2, and 4, negative 2. So these are all your ordered pairs, okay, in that particular graph. And letter B, let's put that set of ordered pairs into a table, and this is how it looks like, okay. And letter C, as mapping, if you put it as a table, it becomes easy to map now. Now, if you notice in the mapping part, you only write your 1 once, and then you just put 2 arrows to indicate to which y coordinate it corresponds to. Okay, so your 1 is written only once, even though it's written twice in a table, and then you just place 2 arrows. And in the same manner, if you look at negative 2, okay, it is also written as once, but you indicate an arrow for 3 and 4 that points to negative 2. Okay, and that's how you do mapping. And finally, determine the domain and the range. Okay, so your domain are all your x coordinates, which are negative 3, negative 1, 1, 3, and 4. And the range are all your y coordinates, which are negative 2, 1, 2, and 3. Okay, and that is example number 1. Let's take a look at the next one. And the next one, in real-life situations, you may need to select the range values for the x or the y-axis that does not begin with 0 and does not have units of 1. What does that mean? Let's take a look at example number 2. To protect endangered species, there is a limit to the number of animals that can be exported to other countries. The table below shows yearly quotas for the number of wild crocodiles that could be exported from Indonesia. Okay, so let's take a look at this table. Maximum exportation of crocodiles from Indonesia, 1986-2000, 1987-2000, all the way to 1994, 1,500. So the biggest ones were around 1988, 1989, where you can export around 4,000 crocodiles from Indonesia. Okay, apparently it's not endangered because they're exporting a lot of crocodiles. Okay. So letter A, determine the domain and range of the relation. Okay, again, this is a relation simply because the 2 factors, year and number of crocodiles, okay, are related to each other. Okay, in terms of how the number of crocodiles is dependent on the year. Okay, and graph the data. And letter C, what conclusions might you make from the graph of the data? Let's take a look at letter A. It says here, determine domain and the range. That's easy enough. The range, the domain will be the years, so from 1986 to 1994, and the range will be the number of crocodiles from 1,500, okay, going from these 2 graders all the way to 4,000. If you notice, you don't write 4,000 twice or 3,000 twice, or 2,000 twice. You only write it once. Okay? So, with that said, let's go to example B. Let's answer letter B, graph the data. So when you graph the data, the values for the x-axis need to go from 1986 to 1994. So again, it is not efficient to begin with a scale of 0. Okay, so the values in the y-axis need to include values from 1500 to 4000. Again, you can include 0 and use units of 500. So what is it saying? Something like this. Okay, so it's not efficient to start from 0 to 1986. So we create a break so that this graph will not become misleading. So this one is fine, your vertical axis, because you can start 0, 500, all the way to 4000, intervals of 500. Okay, again, a jagged line is used to represent the values prior to 1986 that have been omitted in the graph. Okay, and let's answer letter C. What conclusions might you make from the graph of the data? Well, the number of crocodiles that could be exported rose to 1988. It has decreased since 1991. This may indicate that crocodiles in Indonesia are even more endangered, okay, than we think. Okay, so that is example number 2. And let's go to inverse of a relation. So the inverse of any relations is obtained by switching the coordinates in each ordered pair. Okay. For example, in this case, let's say our relation has ordered pairs 1, 4, negative 3, 2, 7, and 9. Okay. And if I graph them, 1, 4 will be here. Okay. Negative 3, 2. Negative 3, 2 will be here. 7, negative 9. 7. Negative 9 will be here. Okay, that is the relation. Now the inverse of that relation would be the opposite, or the switching the coordinates in each pair. So you now have 4, 1, 2, negative 3, negative 9, 7. So the inverse of the relation will now be in blue. 4, 1 would be here. 2, negative 3 will be here. And negative 9, 7. Negative 9, 7 will be right there. Okay, so the red is the relation, and the blue is the inverse of the relation. Okay, and if you notice, the domain of the relation becomes the range of the inverse. Similarly, the range of the relation becomes the domain of the inverse. And we can now define the definition of an inverse of a relation, or we can now find the definition of the inverse of a relation, which goes something like, where is that thing? Okay. Hold on. Okay, so the definition of an inverse of a relation goes something like this. Relation Q is the inverse of a relation S if and only if for every ordered pair AB in S, there's an ordered pair BA in Q. That means you are simply reversing the order of your ordered pair. So instead of AB, it becomes BA. That becomes the inverse of your relation. Now let's take a look at example 3. Express the relation shown in the mapping as a set of ordered pairs. Write the inverse of the relation and draw a mapping to model the inverse. So you have this mapping model, okay, and we want to get the inverse of this. That means everything in the y should go to the x, and everything in the x should go in the y. So the mapping shows the relation of 1, negative 3, 2, negative 2, 3, negative 1, and 4, negative 1. So that if we reverse it, and we take all the y coordinates, put it in the x coordinate pile, and all the x coordinate, put it in the y coordinate pile. Okay, we now have negative 3, 1, negative 2, 2, negative 1, 3, and negative 1, 4. So the mapping at the right shows the inverse. So from there, okay, this is now the mapping of the inverse of this particular relations. Okay, so relations and their inverses display some interesting, okay, characteristics, as we will find out later on. Okay, and that's the end of our lesson. Thank you for watching.